Hello, everyone. Again, welcome to Tamanna and Anuroto, our two bright young scholars who are our guests today. And I would like to read the brief bio. Now, I would like to read Anuroto, your bio. Anuroto is a CS PhD student at North Carolina State University with a research focus on applying AI and ML in solving problems in educational settings. Her current projects showcase a strong emphasis on creating interventions that respect and preserve student privacy and achieve better learning outcomes for students. She completed her master's at Clemson University, where she explored human behavior patterns in online platforms. Prior to, prior to that, she passionately worked on the deeper investigation of autistic children's education from the school and parents' perspective. She has also been actively involved with Women in Computer Science, also known as the ACMW chapter at North Carolina State, and is the graduate student representative of the Computer Science Department in her free time. She enjoys playing ping pong and hiking. Thank you, Anuruddha, for joining us. Now, Anuruddha, please feel free to start your slides.
Sure. Thank you. Thank you so much, Dr. Rahman. It's a pleasure for me to be here today and share my research with you all. And I'm also thankful for not only the opportunity to be here and talk about my research, and also to Dr. Ahmed for his mentorship and his collaboration in my early days of research. So hope you see my screen. Okay. All right. I think I have everything. Okay. Awesome. All right. So the title of my talk today is Learning Ecosystem Revisited with Online Classroom Data in AI-Assisted Platforms. So let's start with an interesting statistic. Did you know that with the transition to online learning from traditional learning, the education sector now generates an astounding 2.5 quintillion bytes of data every day? To put this into perspective, 1 hour of streaming HD lecture generates 1 gigabytes of data based on views, clicks, and other interactions with the system. Attending daily for a year means 365 gigabytes, enough to fill a laptop. Now let's do a quick math. Multiply 365 gigabytes by millions of students worldwide, and voila. Whereas human brain can store around 2.5 petabytes in our lifetime, that is like 15 zeros after 1, add 3 more zeros, and we generate 2.5 quintillion bytes a day. Today, let's take a look at these tons of online classroom data from an AI/ML perspective to revolutionize the traditional teaching methods and learning environments which built up the education ecosystem. As Dr. Ahmed introduced, I'm Anuroto, and my research lies between the intersection of computing education and machine learning. So what can data do? More data means more opportunities for data-driven analysis to improve students' learning experiences and enable instructors and institutions to provide personalized feedback. Now, for a second, let's assume us to be freshmen taking multiple courses, and as the quarter approaches to an end, we are already scratching our heads thinking which courses to take like next semester or next quarter. And thanks to emerging AI/ML techniques, it is possible to get access to all our digital interaction data from multiple classrooms we took part in. And recommender systems analyze the aggregated data, find the frequent and recurrent patterns in our responses and performances, and get recommendations about future courses. Now, wait a minute. I said data from different sources need to be brought together before ML models can analyze patterns and generate personalized results, right? And I smell trouble. A quick show of hands, who knows about FERPA? It's all right. It's all right if you don't know it. FERPA is the short form of the Family Educational Rights and Privacy Act. It is a federal law that protects the privacy of students like us and our educational records. So educational data are strictly private and come with costs. So with this centralized ML approach, right, data from multiple sources are accessed and analyzed, resulting in a breach in privacy, right? What if instead of bringing all data to a single location for pattern analysis, we keep data local and the global model trains all the local entities separately, right? Introducing a distributed machine learning framework here, which is called federated learning, to address this data privacy concerns. Let's take a look at this diagram. Let's say the institution, it can be any institution, any educational institution, it has a central server, right? And a model, which we call as a global model. The global model has a copy in the local settings, as in with each of the classrooms. Each classrooms has their own sets of data that do not leave the respective classrooms. Locally, the ML models are trained separately with the data specific to the classrooms without the need to share the data with the central server. Instead, the model parameters, as in like model weights and biases and all of that that we need for training, are transferred back and forth between the global model and the local models for multiple iterations. Finally, the global model here considers all the local model updates and modifies itself as the federated model. And this framework preserves privacy of the wealth of data, right? And so federated learning has the potential to offer a privacy-preserving, distributed, and unbiased learning platform, which we talked about in this paper that came out last year in AAAI. So you can take a look at this paper where you will find like different use cases we talked about involving stakeholders and possible future directions involving FL in education. Now, if the privacy concern can be alleviated with the deployment of FL or federated learning in education domain, as computing education researchers, we can propose solutions to existing problems for better learning gains of students. A critical problem in this domain is to predict the peers the students will collaborate with for academic success. Now, for the sake of analysis, if we map student interaction data, right, in online classrooms into graphs like this, we get social networks, right? So then we can find patterns in student connectivity, focused communications, and develop their learning skills through collaborations. More importantly, unlike current approaches, this process keeps student data private while future links are being predicted. Let's elaborate that a bit. There has been research done on online social networks, or commonly known as OSNs, and how members of the network can develop social skills via shared connections. And social learning networks, or SLNs, are a specific type of OSNs that facilitate learning through interactions between learners, instructors, and learning modules. It emphasizes social interaction and collaboration as key components of the learning process that can enrich their learning outcomes and experiences. These social learning networks are essentially graph-like data structures, as you can see in this figure. They illustrate learners as the nodes and their interconnections as the edges. A key way to boost their usefulness is by predicting this future connectivity or future links based on inherent patterns of connectivity. While existing work shows SLNs representing online classrooms or hybrid classrooms can help predict future connections, they build their work upon centralized ML methods where either data from multiple sources are aggregated or analysis is carried out on an individual class, right? While the aggregation offers a wealth of data, it might not be practically infeasible due to privacy concerns, right? Whereas the isolated data sets might not contain enough nuanced information across multiple classrooms. Distributed ML here can prevent sharing of raw data of students' peer-to-peer interactions that are highly restrictive for public exposure and usage. We specifically apply federated learning in our research, which has been applied in other domains, but the intersection of federated learning and social learning has not been studied before. So our paper that was recently published in Educational Data Mining Conference, we proposed a novel framework combining federated learning and social learning for link prediction tasks. I will briefly discuss our method and results today. For more, please read the paper. So what kinds of links are these, right? Links are student connections formed, let's say, based on online forum or Piazza or Moodle interactions, or it can be any other learning management systems. Here, we see two sample screenshots of a Piazza platform. On the left, you see that a student and the instructor has responded to the original poster, excuse me. And on the right, there had been 3 different individuals replying to the original post by one student. So in our study, regardless of the contents, these bidirectional links refer to the interconnectivity of students making replies or follow-ups to the original post. We also dropped the connections with instructors because, hey, everyone wants to connect with the instructor and it doesn't give us anything, right? And we also didn't consider the self loops because that also doesn't give us anything. Moving on. Talking about the graph-like social learning network structure, I just mentioned a couple of slides back. So let's take a look. As time progresses, it is highly intuitive that connections among students develop, right? For example, at an earlier time step, as you can see on the figure on the left, 6 students were connected, right, with each other, and more connections were established at a later time. You see, now connections once formed cannot be delinked. That's one of the assumptions we had in our research. Moving on, we had 5 data sets that we did our analysis on. So we had data from 4 classrooms that were collected from massive open online courses or MOOC, like Coursera, edX, or any such platforms. And one was from a real world classroom. We also had STEM course, as in algorithms and machine learning. We also had a couple of non-STEM courses to analyze, like English composition and Shakespeare in community. Let's talk a little bit about the model details. I won't go into deep, but just for the sake of understanding, like what type of models we use for the evaluation, here they are. We had a convolutional neural network all through, and the framework for this paper was built on these 5 models. The first model was a centralized model, which is a single model that is trained and tested using the aggregated data from the 5 distinct classrooms. And then we had Fed average. Fed average is the vanilla federated learning global model after rounds and rounds of federated learning was complete. And the third model, which is federated averaging plus fine tuning, which meant that the global federated model was locally fine-tuned in the local setting with the local data once again, so that locally the model was more adaptive to the local settings. And the fourth model was a personalized federated averaging agent-free model, where we applied meta-learning, which meant that the global model knew what to learn and learned how to learn locally, which gave us more adaptive local models. Finally, we had Fed-ALA, which is federated adaptive local aggregation. So here's the catch. Here, the local model did not blindly follow the global model. Rather, it could select the features it wanted to learn from the federated model. And the results showed that the Fed-ALA model was the best in terms of accuracy. We saw that accuracy is the number of correct predictions by total number of predictions, right? So here you can see that among the 5 models, FedALA achieves the best performance across all the methods for all the classrooms with the highest accuracy. We also took a look at fairness measure, which is the metric of equal opportunity difference. So before that, let me talk about TPR and FPR. So I'm sure we all know about the true positive rate and false positive rate. So true positive rate here was the measure that assessed the model's ability to correctly identify students who form links. And FPR was just the opposite, like evaluating how often students not connected are incorrectly classified as link forming. So EOD, or equal opportunity difference, here was based on the quantification of these two measures. It measured the difference between TPR or FPR values across the classrooms, referred to as the range of TPR or FPR. In this figure, you will see that we compared how close TPR and FPR were across the classrooms, right? A smaller range of TPR is desirable as it reflects more consistent positive predictions across different student pairs belonging to different classrooms, and it contributed to model fairness, right? The most fair model would have a range of 0, meaning like across all the classrooms, the prediction is just the equal. And this also means that regardless of the communities students belong to or represent, FedALA does the best job at correctly forecasting links among the student pairs. So what are our takeaways from this? With online learning gaining popularity, tons of private and expensive student and system interaction data are being generated. As much as they make students' lives convenient by finding patterns in large data sets and offering tailored recommendations, they cost our privacy when our data are accessed and shared by the models. Federated learning can provide a privacy-preserving platform here to improve the learning ecosystem for online classrooms. This distributed technique exchanges machine learning model parameters rather than data, making the students and the instructors feel safe in digital environments. Variations of federated learning have shown to outperform the centralized method I just talked about in terms of performance and fairness when it comes to predicting future connections among students in classrooms. Biases due to lack of data were not a concern here. This suggests that it is better at serving students with diverse, non-dominant learning patterns, including those from marginalized or underrepresented groups. Our future work focuses on using such peer-to-peer relationships for better learning gains. That's all. I'm happy to take any questions.
Thank you, Anuradha, for your excellent presentation and excellent research.